Hi, I'm Jicho Kim from the University of Connecticut. Today, I'm going to talk about my research on dynamical systems modeling of human metronome phasing performance. First, I would like to thank my co-authors, Kat Hall, Alex Paxton, and Ed Large. And I also like to thank Yi Wei and the members of the Music Dynamics Lab. Phasing is a compositional technique that has musicians playing identical patterns move in and out of phase from each other. In Steve Reich's drumming, two drummers start playing the rhythmic pattern shown here in unison. Then they gradually desynchronize, with one drummer slightly increasing the tempo, while the other drummer holding a steady tempo. Here is a demonstration. In a previous case study, two Reich experts, Russell Hartenberger and Bob Becker, recorded the phasing section from drumming. The figure on the top right shows the metrical positions of the drummers over the course of phasing if they follow the instructions in the score. As shown on the bottom right, however, what really happened was that the drummers sped up and slowed down together throughout the phasing section. We analyzed the performance data further and found systematic nonlinear trajectories of the drummer's tempi and relative phase. Zooming into the first portion, as the moving drummer increased the tempo, shown in red, the steady drummer followed suit, shown in blue. As a result, the relative phase did not advance at first, shown in yellow. But when their tempi diverged eventually, the relative phase advanced to another plateau, while the drummers slowed down together. We suspected that the interesting nonlinear trajectories result from the coordination dynamics where the voluntary intention of desynchronization interacts with the involuntary tendency of synchronization. We tested this idea with a model of two mutually coupled oscillators. By introducing frequency increase or bias in one oscillator, we were able to replicate the nonlinear trajectories found in the human expert performance. In this study, we used phasing as an experimental paradigm to extend and generalize the findings from the expert case study. We studied coordination dynamics when participants intend to desynchronize with sensory input, which is quite a different situation from typical sensory-motor synchronization tasks. As a first step, we simplified the task in two ways. We studied phasing with a non-responsive partner, a metronome, which generates an isochronous rhythm. We also wanted to test non-experts, so we recruited from the UConn's Psych Department participant pool. 6 out of 27 participants reported little to moderate level of musical experience, but none of them were music major students. The experiment started with a verbal description and audio-visual demonstrations of phasing. The participants then practiced phasing with an interactive visual display in practice 1 and with a feedback on their performance in practice 2. Then they did 21 trials of phasing for 7 metronome tempi from 80 to 140 beats per minute. The schematic shows the structure of each trial in practice 2 and the main experiment. The participants were instructed to start tapping in phase with the metronome, and upon hearing the cue sound, begin phasing in a steady but self-paced manner. Once they complete one phasing lap by coming back to in phase, they were asked to tap a few more times and stop. We asked the participants to phase in a gradual and controlled manner and provide feedback on the number of phasing laps and the number of taps after each trial in practice 2. No feedback was given during the main experiment. We analyzed the phasing data in the following way. We first calculated the relative phase of each tap from the timestamps of the tap and the closest metronome tick. Phasing lap displayed on the vertical axis is simply relative phase divided by 2 pi. Then we determined the range of relative phase for initial in-phase tapping, from which we obtained the final target range. The phasing window, indicated by the pink area in the plot, included taps between the initial and the final in-phase ranges. Then we counted the number of taps in the phasing window and the total number of phasing laps made in the trial. In this particular trial shown here, 15 taps were made during phasing and only one phasing lap was made. We found three types of phasing performance. In successful trials, only one phasing lap was made, conforming to the task instruction. Only 38% of the total trials were successful, indicating the difficulty of the phasing task. The trials with more than one laps were named unsuccessful, and they accounted for 41% of the trials. Here, a trial with 4 phasing laps is shown in the middle. In 19% of the trials, no complete phasing lap was made, and hence we call them incomplete. In this talk, we will focus on modeling these three behaviors. Before moving on to modeling, let me show you an interesting finding. We may use the number of taps per phasing lap to measure how gradual and controlled phasing was. As shown on the left, we found the average number of taps per lap was the largest for the successful trials and was significantly smaller for the unsuccessful trials. The same relation was also found at the participant level. As shown on the right, the participants with a higher percentage of successful trials performed more gradual phasing. As you can see here, the amount of musical experience did not correlate with the success rate. As we did for the expert case study, here we aim to model the human metronome phasing data in terms of the interaction between intrinsic dynamics and intentional control. We use a phase oscillator coupled to a metronome signal as a minimal model and introduce frequency increase or bias as the effect of the intention of phasing. The oscillator can desynchronize with the metronome, in other words, escape the in-phase attractor when the frequency bias is strong enough. We may characterize the three types of phasing behaviors in the following dynamical systems way. An incomplete trial shows a dynamical system that is unable to escape the attractor at the origin. To use an analogy, it's like a car trapped in a valley, unable to climb up the hill. An unsuccessful trial shows a system with high kinetic energy enough to escape the original attractor, but is unable to stop at the goal attractor, like the car on the right which overshot the stop sign. To perform successful phasing, a context-sensitive control of frequency bias and/or coupling is required, because the attractor you want to land on is the same attractor you escape from. A simple way to model the incomplete and unsuccessful behaviors is to assume a fixed amount of frequency bias. The plot on the left shows the synchronization region for the phase oscillator model in the equation. For a given amount of frequency bias indicated by the red dashed line, the system may or may not be in the synchronization region shown in orange, depending on the coupling strength. When the coupling is strong, marked as A, the oscillator cannot escape the in-phase attractor, showing the incomplete phasing behavior. When the coupling is weak, or when the oscillator can ignore the metronome signal, it can escape the in-phase attractor, but it does not stop after one phasing lap, showing the unsuccessful behavior. Successful phasing can be achieved by a context-sensitive control of frequency bias. This is an area of skill and strategy, so there are many possibilities for underlying mechanisms. Here we test frequency dynamics that attempt to maintain a constant rate of relative phase increase. As shown in the red curve in the plot, this results in an initial increase of natural frequency, followed by a decrease. Again, we can use the car analogy to understand this. To maintain a constant speed, you have to press the gas pedal going uphill and put the brakes on going downhill, because the same attractor can pull you back or push you forward depending on the situation. Notice that the relative phase trajectory shown in blue on the right is not completely linear due to the presence of the in-phase attractor. Lastly, we model the antiphase plateau often observed in the human data as shown on the left by introducing higher order terms shown in pink in the equations. Similar to the classic HKV model of bimanual coordination, these higher order terms introduce an attractor at the relative phase of pi or the phase lap of 0.5. The model simulation shown on the right now has a slowdown of phasing near the antiphase relation. I hope we showed you that dynamical systems theory provides intuitive concepts and meaningful models for phasing performance. Compared to the expert performance examined previously, the current non-expert data reveal more about phasing dynamics and tell us what is needed to perform phasing successfully. However, the difficulty of phasing tasks led to high variabilities in the data. Multiple longer training sessions would be necessary to train non-expert participants. And a longitudinal study could show how phasing dynamics change as the skill is acquired. We are also planning human-human phasing experiments to study interpersonal coordination. We also plan to study phasing with musicians, especially percussionists, in a controlled experiment. Thank you for your attention, and we look forward to hearing your questions and comments.